For today's session, we are going to learn how to model this beam in Abaqus environment and how to establish bending moment and shear force diagram in the Abaqus environment. So just observe the configuration of this structure. There is fixed support, two hinges in the middle of the beam, and then there is this clockwise movement being applied on support B, and then there is uniformly distributed load, and at the end of the overhanging part there is 35 kilonewton force uh, applying downward. And the first part of the structure is 4.5 meter long, then 6 meter long, and then 9 meter long. And we are assuming that this cross section of the beam is 200 by 400 millimeter. So, and the beam is made up of steel. So now, as we have established all the requirements, let's move towards our Abaqus. So first of all, you need to create a part. Since the analysis is in the 2D environment, or we are just considering x and y axis, we are not interested in the third dimension, so it is 2D planar, and we are selecting it as a wire. The length of the beam, total length of the beam is 19.5 meter. So let's consider this approximate side as 20. And one thing that you need to do throughout in the modeling process and in the analysis part, that you should be consistent with unit. If I'm selecting, if I'm assuming that I'm going to be in meter, then you can't be in millimeter in any at any step. So let's move toward let's moving forward. The approximate size 20. Now let's make the beam. So first of all, the first part, the second part, and the third part. Right now I'm not considering the dimensions. I will edit the dimension through this tool. So 4.5 millimeter, the first part, 6 meter, the second part, and 9 meter, the third part. So there is my beam. So done. There is my beam. Now second, properties. First of all, let's define a material. As I have already told you that it is steel, I'm going to enter the properties of steel. The mass density of steel is 7,800 kilogram per cubic meter, and it is elastic modulus 200 Newton per Newton per meter square, 200 10 to the power 9, and Poisson's ratio is 0.3. Why? Poisson's ratio. What's the issue? Alright, now the steel material has been defined. Second is we need to define the orientation as well. This is very important step that you assign a beam section orientation. And before doing this, you need to define section. So let's create a section. Select beam category, and it is type beam. Continue. Here you need to define your profile. So create a beam profile. It is rectangular. The beam is rectangular. And the A part is, I have already told you, it is 200 millimeter, 200 by 400. So A part is 200.2 and the B part is 0.4. Click OK. Alright. This is steel. Alright. Everything is good to go. Now, you can assign a section. Select your beam and assign the created section. Bingo, you have assigned your section. Now you need to assign beam orientation. It is very important step, so you should not miss it. 0, 0, -1. Okay, done. We have defined our beam section orientation as well. Now, let's import it in the assembly, and it should be independent mesh on instance. Okay. So now the beam is in the assembly. Now let's define a step. The already initial step is being there. This is for boundary condition, but for the loading we need to define a new step. So you should select static general. Procedure type is general. So let's continue. Leave like do not um, um, alter any or do not make any changes here. Leave everything as it is, and here you have this is step 1. Now let's go towards load. Here you will here you will define boundary conditions and load. So first let me define the boundary conditions. Boundary condition always will be defined on initial step, and it is displacement rotation. Continue. The first, it asks me to select the nodes where I'm going to apply my boundary condition, and since the first node, the first support is fixed, so I'm checking all the boxes. Now let's define second boundary condition. Here my second support lies, and it is pin, so I'm just checking the 2 boxes. Then let me define my third boundary condition. It is the support is here and it is pin, that's why U1 and U2 are being checked. Now after doing this, let's define the loads. So the first load is M or moment. Now you can't apply load using step initial. You need to select step 1 that we have already defined, and it is mechanical. Movement, continue, select the node where you are going to apply the movement, and here it is clockwise movement, that's why I'm selecting I'm entering in negative 50,000 Newton meter. Okay, now define another load. Now the load is line load, UDL. Let's write in the capital letters, UDL. It is asking me to select member, so I have selected the member. It is component to obviously, minus 10,000 Newton per meter. It is showing me as well that the loading has been defined. Now the last loading is point load. So this point load, concentrated force, select, and then select the node where you are going to apply this concentrated force, and you know it is minus 35,000 Newton. So I have defined this, the loading part. I have done with my loading part. Now let's move towards mesh. In order to do mesh, first of all, select the element type, select beam. It is beam. Make sure that it is a standard beam and linear. In such kind of problem, this is the perfect. Select the region to be assigned element type. Select the region. It's okay. And then you can do mesh instance. Before doing the instance, let's do the seeding. And I'm like the mesh size, how much the mesh size should be. I'm 40 mm. That's 40 mm. And now mesh instance. It is asking me okay to mesh the part instance. Yes. So 49 elements have been generated on instance. So Meshing is done. Now, the last part, which is to create job. Let's create a job, leave whatever it is there as it is. It is full analysis, background immediately. And the general part is all. Everything should be put as on default. Um, let's submit it and hope that there will be no error. So it is completed and thank God there is no error. So this is our result part. This is our deflected diagram and as you can see it is correct. Alright, one thing that I missed that you need to set what kind of outputs you want. So in order to set what kind of outputs you want, you should go to field output request and here you need to create a field. What kind of reactions do you need? Force and reaction forces and moments. Obviously, we need to look into. And then, in addition, nodal forces and beam section orientation. Remember, we have defined beam section orientation so that we can get nodal forces, right? Here you are getting why I have done that. So, all right, good to go. So, after doing this, I guess I need to run my analysis again, submit it, okay, so it will run. As the analysis is done, it will inform me. The status will be here, completed, and here as well. Alright, let's move to the results part. So here I can select what kind of input I need to know. CF is basically the reaction. Here I can observe my reactions. Obviously, I need to CF2, CF1, and then movement. Alright, in order to plot bending moment and shear force diagram, in order to observe the reaction forces more clearly, you need to do something. You need to create a path. So how to create a path? Just go in the path. It is path, add before, and now you should create a path. So let's first of all let's fit the image perfectly, and then it will tell you where to select. These points will be at every seeding point. As you move forward, it will tell you where to select, right? And it is basically, it is at every seeding point. That's why you need to enter the match size very intelligently so that no point should be missed if you are plotting shear force and bending moment diagram. Right, everything is done. Okay, path has been created. Now go into the tools, XY data, create. We are creating from the path. Field output. Let's create our shear force diagram first of all. Plot. This is our shear force diagram, right? And if I need to see my bending moment diagram. This is my bending moment diagram. And if I want to see what kind of reactions do I have at nodes. It's not clear here. There's something wrong here. However, like if you need to know the shear force and here it is not point loads at node, no, not this. The reaction forces at node. So now if you plot, you will get the required data, right? The reaction force here and the reaction force here. Remember, if you notice one thing, the reaction force at 4.5 is missed. And why it is missed? Because the seeding was not in such a manner that it doesn't catch this particular point. So that's why the size of the seeding or the size of the mesh is very, very important. And you should select it very carefully. All right. This is all about for today. We will do some another examples sometimes later. And let me end this session with our bending moment diagram, which is this. This is my bending moment diagram here by the program and 10 raised to power 6. Remember these, and these are not in point. Point multiply 10 raised to power 6. And it should be divided by 1000 so that I can uh, get my answer in kilonewton meter. And if I look into my hand calculation, then I can see here. This is my bending moment diagram. And this is what exactly I'm getting here. Right? So here I'm concluding my session. Hope so you have learned from it.